going to cover the other type of transistors that we alluded to last week. We covered MOSFETs and those types of circuits all last week. And this week we're going to talk about bipolar junction transistors, which are different. They do do kind of similar things, but they are constructed very differently and are useful in different arenas. So a bipolar junction transistor is basically made using three different semiconductor regions. You can either put N material, P material, then N material, or P, N, and P. So there's two basically versions. There are three terminals that connect. There's the collector, the base, and the emitter. So the collector is similar to the drain in a MOSFET. The emitter is similar to the source. And then the base is similar to the gate. But the way it's controlled is different. The MOSFET was controlled by voltage at the gate. The bipolar junction transistor is often controlled by the current going into the base. So unlike a MOSFET, there is current going into the base of this device. So it's not going to have the same effect. The emitter is the most heavily doped, then the base second, and the collector third. So unlike a MOSFET, it's not the same. It's different. So it really can't be turned around backwards. It wouldn't work the same way at all. So to start with, we have three regions: the emitter region, the base region, and the collector. We have metal contacts where there are terminals, and the three terminals are labeled as shown. So this is really different and probably a lot simpler to look at than the MOSFET. Remember, the MOSFET, all kind of weird depletion regions and channels, and we don't have that. There are two PN junctions we deal with. There's the emitter-base junction, which is obviously between the emitter and the base, and then the collector-base junction, which is between the collector and the base. Those two junctions are going to be important in how the device works. Either of those junctions could be forward biased or could be reverse biased, depending on what voltage is applied. Technically, you could say that there would be four possibilities since each junction has two possible states, but in reality, there's really only three that are used. And when we get to, this is just the PNP, it's really the same thing. When we get to looking at them, you'll notice that the modes include the junctions being both reverse biased or with the emitter base forward and the collector base reversed, or with the emitter base forward and the collector base forward. You'll notice there's actually not a reverse forward option. Reverse forward would be called reverse active, says because it would basically reverse the conditions of the active, and that's something that technically could be done but isn't. So active mode is if you have an amplifier, that's what you're going to have to use. And then cutoff and saturation, actually, since they're kind of opposites of each other, they are actually used as switches sometimes. So at cutoff, there is no current, and then at saturation, there's maximal current. Now, I will warn you that when we look at the characteristics of the current and the voltage, it's going to look really similar to a MOSFET, and it is really similar to a MOSFET. You're looking at base current instead of gate to source voltage, but other than that, we're relating the collector emitter voltage and the collector current, which is similar to relating the drain to source voltage with the drain current. So that is similar. However, for whatever reason, while MOSFETs were amplifiers in the saturation region, BJTs are not amplifiers in the saturation region. So saturation for a MOSFET means something completely different than saturation for a BJT. And that's just one of those things. It has completely different meaning. So when we look at how a BJT is working, if we want to use it as an amplifier, we're actually going to have to use it in the active region, whereas that was similar to the saturation region in a MOSFET. Where it's operating is just something called the Q point, and then the Q point current and voltage are just related to that particular point in which it's operating. And when you take a course in amplifiers, then you learn why it's important to put the operating point like in the middle of the active region. But for now, we're not going to talk about that. So we're going to talk about the active mode. The active mode for a BJT transistor is when the base emitter junction is forward biased and the collector base junction is reverse biased. So that's what we need in order to make this work as a amplifier. You will notice too, there's all kinds of currents and junctions and arrows and stuff, but it's not as bad as it looks. So first of all, you'll notice that there is an emitter current, there's a collector current, there's a base current. We don't study those in quite as detailed as we do when we get to engineering electronics, because we don't really put these devices into circuits. So don't worry so much about the currents going around on the outside. Pay more attention to the inside. When we start out, you'll notice that in the N++ region, there are electrons that are majority carriers. And when we apply voltage and we forward bias the PN junction, that means the electrons are moving in the other direction. So the electrons are moving from N to P. And so they get pushed over into the P region. They become minority carriers. And when they are minority carriers, some of them combine with the holes, because there's a lot of holes in the P region. And when they do, there's a current that comes into the base to replace those holes that were lost. So there is actually a current that's drawn to replace that. Then the rest of the electrons that were minority carriers just keep on going, and they end up in the N region, the collector region again, and that's why it's called the collector, because it's collecting electrons. And they're majority carriers again, and then it just keeps going round. And notice that, of course, the actual current directions are opposite from the electron flow. So the other thing that happens is majority holes from the base region also end up in the emitter region. Some of them do. They get pushed there. They become minority carriers. And so again, there's more base current that comes in to replace that. So there was an IB1 and an IB2, and both of those are turning in, basically are causing that base current to be drawn. Then the movement of charges, the reason the charges move the way they do is because of the doping concentrations of the regions. So it wouldn't work the same way if you just had PNP and they were all the same. It really has to have differing doping concentrations in order to work properly. The emitter current is the current, basically, it's the combination of the injected electrons and the injected holes. So it's just the movement of those two that makes up the emitter. The base current is made up of the loss of holes connected into the base, and then also the holes lost due to recombination. And then the collector current is the minority electrons that went across the base and ended up in the collector. So the collector current is just the electrons that make it through the depletion region, and that's all it's based on. So the emitter current and the collector current are rather large. They're usually a couple, 2 to 3 orders of magnitude larger than the base current. So the base current is small. That's why the arrows are small. And the emitter and collector currents are larger because they take more value. They have more carriers. The current, again, flows into the collector. And there is an equation that kind of describes the current. It's similar to diode current. It's the same idea. It's just that we don't have the diode voltage. We actually have the base emitter voltage. And then remember, we divide by the thermal voltage. This is similar to the equation when we had IS times E to the VD over NVT minus 1. That's the same idea as where we get that. So it comes from the same idea because it's a PN junction. The base current is made up of 2 things, IB1, holes injected into the emitter from the base, and then IB2, which is holes flowing into the base to replace those lost. And then both of those are proportional and add up. And If we have a configuration in which the emitter is common to the input and the output, which is a very, very common way to have a transistor hooked up, then the ratio of the collector current to the base current is equal to something known as the common emitter current gain, or beta. Beta ranges from 50 to 200, and it's generally given on a transistor's spec sheet. It's called HFE, and I'm not going to explain why. It relates the input and the output. So what this means is that if you have a bipolar junction transistor and you know the value of beta, you can relate the DC collector and base current with that value. The emitter current is just the sum of the collector and the base current, and we can actually use beta to relate the base current to the emitter current as well. Sometimes we like to actually have the base common to both input and output, which sometimes happens, and then we have a base current gain known as alpha. And alpha you can actually get from beta over beta plus 1. So as you can imagine, since beta is a relatively large number, between 50 and 200, beta over beta plus 1 should be just less than 1. And it is just very, very close to 1. This is a kind of a summary of all the parameters for BJTs, all the parameters you should ever know. And it works the same way whether you've got a PNP or an NPN transistor. It's just the current directions are different, but everything else is the same. So briefly, just going through the PNP active mode, I'm not going to dwell on it for a long time, but you notice it's exactly the same, except it's holes instead of electrons. So you have majority holes going to minority holes going over and becoming collected as majority holes again, and it's really the exact same thing. It's just that you have holes and electrons switched. And in saturation, so this is a different mode. In saturation, the emitter-base junction and the collector-base junctions are forward biased, and that means the transistor's on as far as it can go. So it's sort of similar to when we talk about saturation in a MOSFET, in that the current is as high as it can go. But in this case, it's basically the transistor is on and the collector current is as big as it can possibly be, and the voltage between the collector and the emitter is really, really small. What happens when this happens is that the base current ends up changing to adjust, and this means the beta value actually changes. This is something known as the forced beta, and again, we're not going to dwell on it for a long time. Just know that the value of beta changes when you go into saturation mode. So beta really is only useful when one is in active mode. As with the MOSFET, this is what the symbols for the NPN and PNP look like. The NPN has the arrow pointing out and to the emitter, and the PNP has the arrow pointing in from the emitter into the device. And if we wanted to use these as an amplifier, which we do quite frequently, basically VBB and VCC, so you have two voltage sources. There are ways to do it with only one, but again, we're not going to talk about that. They're used to forward bias the base emitter junction and reverse bias the collector base junction. So that means at the base there is a DC voltage, and that DC voltage is equal to VBE. Since this is a forward bias PN junction, VBE is generally, because it's usually silicon, is about equal to 0.7 volts-ish, more or less, because it's a silicon PN junction, and that's what you get when you forward bias a silicon PN junction. So that value of VBE is used when we add an AC source. The value of VBE pushes the average value up, meaning that that input voltage can kind of vary VBE a little bit without reverse biasing that junction. So Vin has to be really small. VBE is only 0.7 volts, so Vin has to be small enough so that it's not going to push that junction into a reverse biased condition. So if that's done, and if you have the proper input voltage, what you get out is found at the collector emitter voltage in VCE. That's going to be a much bigger voltage than VBE. It's generally a good value is about half the VCC supply voltage, so it can be, relatively large. And that supports the variation at the output, again, without changing the bias conditions. So VCE is the DC voltage between the collector and the emitter, and what you get out is, again, an output that needs to go positive and negative, but not change the bias conditions of the junctions in the circuit. You'll notice that the output in this case is flipped over as well, and that's because a amplifier made this way actually ends up giving you an inverted output. Again, the reasons for which you learn in engineering electronics, not in this class. So that is all we have to say about transistors, MOSFETs, and BJTs, and we'll see you next time.